Okay. So for us, H is L2 of Rn for some n, which we identify with the gamma of Cn, the Fock space of Cn. And we have these Weyl operators, alpha and Cn, which satisfies the Weyl commutation relation. And using that, we get the family of self-adjoint operators. So P alpha, self-adjoint unbounded operator. With domain of P alpha contains the exponential domain, which is span of E of alpha and C. We have this exponential vectors, and you take the span of that, and that is contained in the domain. And domain is much bigger. This is not actually equal, but the domain is much bigger than that. Okay, such that e power minus it P alpha is our W of alpha. And this P alpha also satisfies this commutation relation, which we will recall whenever we need. Okay. Huh? Say it again. P alpha, right? What did I write? What? W of T alpha. W of T alpha, correct. Right. W of T alpha, correct. Yeah, W of T alpha. Okay, so this is it. And we say a state is Gaussian definition. We haven't defined formally, so we have said it orally several times. A state on H is Gaussian, is said to be Gaussian if the distribution, we have a state, we have a self-adjoint operator, then there is a distribution on the real line. Indeed, on the spectrum of the self-adjoint operator, that is what is called the distribution of this observable P alpha under this rho. A state rho on H, you have a state rho on H is said to be Gaussian if the distribution of P alpha under this rho is normal, is Gaussian, of course. I call it normal. Normal is normal. Okay. On R. Then we say it's a Gaussian state. Okay. This is the distribution. So this is for all alpha. Okay. This is not the usual definition. Let us take this as our definition. The usual definition is as follows. So you have the Cn, let Cn equal to span of Ej, j equal to 1 up to n, where Ej is an orthonormal basis. Okay, where is V is orthonormal basis for Cn. Okay. Then you can define this Pj for physics. For some reason, they have a constant. This is 1 by root 2. 1 by root 2 of P of Ej. This is the, okay. And Qj is equal to, again, 1 by root 2 of minus of P of Iej. This is Qj. So this is what is called position observable, or position operators. And these are what is called momentum operators. Of course, a state is Gaussian. I mean, I have put a minus there. I think the minus is needed. In the paper, there is no minus. But in the earlier book, he uses minus. So I think there should be a minus there. Because when he writes the annihilation creation operators, it is only with the minus that definition is correct. So I think there is a minus. But it meant for our definition, all these things, it doesn't matter really. Okay. So your state is Gaussian if summation xj pj minus yj qj is Gaussian for all z is, same definition, I'm just repeating, for all z is equal to xj plus iyj, j equal to 1 to n. This is in Cn. You have a tuple like this, and for any such tuple, maybe z bar if you want. Okay. This is Gaussian. So it's the same definition. Okay. So I'm just taking the summation like this. Okay. Okay. So, and we have got one, still now we have got, I mean, not one, we have got a set of Gaussian state, which all of them have the same variance. I mean, all of them P alpha as a, well, the variance differs, but what I mean is the covariance matrix, which we will define soon. The covariance matrix is identity for all of them, but the mean is different. Okay. So example, we have already seen this example, which we have worked it out. So if you have rho equal to, you take chi alpha, this vector state chi alpha, where chi alpha, this vector state equal to e power minus alpha square by 2 into e alpha. E alpha is the exponential vector and it has norm e power alpha square by 2. So we have to divide it by that, and so that you get unit norm. And this is a Gaussian state. We have verified that. Okay, so let me add something here. So we have, I mean, I have given you the assignment. I hope you have done it. So your state is maybe a proposition, whatever the fact. Your state is Gaussian. Your state rho is Gaussian is equivalent to saying we have defined the rho hat. Okay, rho hat is the using W of alpha using trace. I mean, rho hat of alpha equal to trace of rho W of alpha. We have defined this rho hat, and this rho hat of T alpha is the characteristic function, is a characteristic function. I mean, this is here the characteristic function is the classical characteristic function. Classical characteristic, or let us just write it. Rho hat of TH is equal to, it is of this form. Let me just write directly the definition. Equal to e power minus half sigma square T square plus I times mu T for some sigma greater than 0 and mu in real line. Okay. So this is the whatever I have written is the characteristic function of normal distribution with variance sigma and mean mu. Okay. So if T alpha, this is for fixed alpha. For all but fixed. Okay, but fixed here. For fixed alpha in Cn. Okay. For all alpha in Cn, for any, I mean, this is for all t. This is for all t. Okay. So if and only if this is. So this I asked you to write it as an assignment. The proof is not difficult. First thing you have to know that spectral theorem, using spectral theorem gives the following. I mean, if you have if you have a state rho, and if you have a, spectral theorem says that any this operator can be written as some use with respect to some dp. Dp you can write it as x dp. Okay, and then if you define mu xy, which is just I mean mu x. Let's take it. I mean it should, xv I am using for Cn. No, so let me use xi eta. Xi eta are vectors in H. Then you can take this P of E eta. Okay. I hope you have done it. Should I go through? So there is no need. Anyway, I will just give them, you just verify you have got the right idea. Okay. So you using spectral theorem, if you have any such, so this gives a complex measure. If xi is equal to eta, this gives a ordinary measure, finite measure. Okay. And when you want to integrate with respect to the finite measure, it is just integrating the function t going to t, that identity function. So it just says that if you have the operator t, if you have p alpha, any operator t, then xi t xi, this is equal to the integral t, this d mu xi xi. This is just the usual integral over R. Okay. So this actually will verify if your state is the xi xi. I mean, the state is given by the pure state. If state is equal to pure state, this will actually verify. I mean, this is actually equal to this is actually trace. Whatever return is the trace when multiplied by the rho with t and other things. Okay, so it will actually verify. I mean, it's not just this e power I t t also. I mean, you can replace this t. Spectral theorem says the following: e power I t t equal to, here you can have the e power I t, e power minus I t. Yes. Here it should be S. Okay. Okay. So this is given by the spectral theorem that will verify whatever the statement for the pure state. From pure state, you have to do some approximation convergence to prove for any state. That's all. Okay. So that's all. So that statement. So this says that, so if any rho is Gaussian, any state is Gaussian, if and only if rho hat of T alpha, rho hat defined the quantum characteristic function is actually, then rho hat is a quantum characteristic function of rho, then that is equal to this. Okay. So now if you take this state, I'm just recalling again. If you take this particular state, then we know that rho hat of alpha is equal to exponential of minus half norm alpha square plus I. It is plus I. It depends on where you put the imaginary part. Imaginary part of this is alpha. Yeah, no, this should be beta. We have already alpha there, so this should be beta. Okay. So beta alpha. I think it's beta alpha. If you take minus, it should be alpha beta. I think. Okay. I hope I remember correctly. Okay. We calculated this. We just went through the calculation and we got this. Okay. So this will imply that under that row, all this, I mean, this is a Gaussian state. This proves that. I mean, if you insert a theta, you will know that the variance will be, variance will be exactly equal to alpha mod alpha, and the mean will be whatever. So this is also equal to, if you want, I times real part of beta j alpha. Okay, j alpha. J is the operator we have used, but you have to consider alpha as the real vector. Okay. So we have got something Gaussian, but this is all in this. See, we want to see later. We want to get our we want to show that it will be of this form, exponential minus. We want to prove this later. Rho hat of alpha will look like this: alpha s alpha minus I imaginary part of something. Okay, where we will have alpha here, and then we will have some vector here. Okay, we want to use it. The point is, see, this is like a multi Gaussian variable with covariance matrix S, and the mean here you have a vector beta, means the mean will be beta, where beta coming from R to N. Okay, and S is a matrix in M to N. It's a real matrix in M to N. Okay, so we want to write it like this. You want to call this as the covariance matrix. Any? No, we want to see what are all the matrices coming. S should be positive to start with. Yeah, our sigma, we get sigma square. A covariance matrix is a positive matrix. So it will be a positive matrix to start with. And we want to get all vector in R2N. We will get all vector in R2N. For example, if you have any Gaussian matrix, see, first to get this, I mean, this is what I mean by some Gaussian, quantum Gaussian with covariance matrix S and mean alpha, mean beta or whatever. If it is of this form, whatever I have written, okay, exponential of minus alpha s alpha plus I times imaginary part of beta alpha. Okay, this is with covariance matrix S, and mean will be j beta, I think. I mean, it's up to j, up to a j. Okay, it's j beta. It doesn't matter. J is a unitary, so you will get all vectors. Okay? So if you have a matrix with mean 0, okay, if you have a matrix, if you have a state with mean 0, then you can conjugate by this. See, we have already proved that if rho is a state. See, we have W of x, rho W of x star. You take the whole hat, okay, at alpha equal to e power. I think there is no I2 imaginary part of alpha x, I think. Okay. There may be a minus, I'm not sure, but okay. We proved this times rho hat of alpha. We proved earlier. Okay. So because of this, if you have some rho, if rho is a Gaussian state with mean 0, okay. If you conjugate with W of x, you will get the mean x there for any x in Cn. Okay. So getting a Gaussian state with any mean in R2n is not a problem. You can conjugate with W of x, and if you have a mean with a Gaussian state with mean 0, you conjugate with W of x, you get a Gaussian state with mean whatever the required mean. Okay. So so we have to see what are all the covariance matrix, what are all the possible covariance matrix, and whether it is possible to get all those things. Okay, so that's what. Whether we will get all covariance matrix, it will not be possible. We will see that it will not be possible because of the uncertainty principle. And whatever the uncertainty principle says, restricts, we want to see whether we can get all those covariance matrix. Okay, that is what the rest of the, our goal is that. Okay. So for the time being, we have got covariance matrix identity. This alpha, norm alpha square is alpha alpha. We have got something with covariance matrix identity. Now, now we have done the following. If we have a symplectic, let me recall what we have done. Should I recall? It's okay, no? We have already done the symplectic thing. So if we have a, anyway, so if S from Cn to Cn is symplectic, if, it's real linear, S is real linear, invertible, okay, is symplectic if imaginary part of Sx, then it should be outside, equal to imaginary part of xy. Okay. Then given any S is from Cn to Cn, we defined S naught of any xy is equal to S naught of xy equal to real part of S of x plus iy, imaginary part of S of x plus iy. So we get a, so S naught is from R2n to R2n. So we got an operator from R2n to R2n. And S is symplectic is equivalent to saying S naught satisfies J S naught transpose S naught is equal to J again. Okay. Which is equivalent to saying J S naught J inverse equal to S naught transpose inverse. Okay. So we have verified all that. And we have proved that S is symplectic is equivalent to saying there exists unitaries U1, U2, and A, a positive matrix. A is in Mn of R such that S is equal to U1, SA, U2. Okay. Where SA acting on X plus IY equal to, it's positive, so I don't have to take the star, A inverse I times A inverse Y. It looks like this. So we have proved this structure theorem. So using this, we define gamma of S is equal to gamma of N. And just recalling what we have done. We define gamma of S equal to gamma of U1, gamma of SA. Gamma of SA is in the assignment. Okay. So once that is done, we get gamma of U2. We have defined something like this. Where this gamma is second quantization for unitaries, and that is the gamma of SA we defined the assignment, and then we got gamma of U2. Okay. Okay. Now we have the following proposition. So rho is a state on L2 of an H or H. Okay. Then gamma of S rho gamma of S inverse hat is nothing but rho hat of at alpha equal to rho hat of S inverse alpha. Same proof. Okay. This is equal to trace of gamma S rho gamma S inverse W of alpha, right? Which is equal to trace rho gamma of S inverse W of alpha. You can take the gamma of S this side. And that is equal to trace of rho W of S inverse alpha. Once we settle this in the assignment, okay, this is equal to rho hat of S inverse alpha. So it's clear. So if you have a state and if you conjugate, if you have a state and if you have a symplectic isomorphism, okay, then you conjugate with the second quantization of the symplectic isomorphism. You conjugate the state with the second quantization of the symplectic isomorphism. Then we get a new state. What you can see is this will alter the covariance matrix of the Gaussian state. Okay, if S is so, if see, you take for example, if your rho is chi x, you can take, I mean, you don't have to worry about chi x because that you get it by conjugating by the Weil operators. Okay, if you, I mean, we let us take the vacuum state. Vacuum state is the E0. Okay, E0. Okay, let rho equal to this. Okay. Then gamma of S rho gamma of S inverse this hat. Then we know that rho hat is equal to e power minus rho hat of alpha. You have already verified. There is no x part. This is equal to alpha square by 2. And this will be equal to exponential minus S alpha square by 2. Sorry, S inverse alpha square by 2. Right? By what we have verified. Okay. Now, if S inverse is positive, I mean, this is equal to what? This is, so this is equal to e minus e power S inverse alpha, S inverse alpha. So S in, if you want S inverse star, S inverse alpha. So now we got a positive matrix here. Okay. So which is, I mean, if it is unitary, that is equal to 1. Okay. So there is no point in conjugating by the unitary gamma of u. If you conjugate by unitary, then you are going to get the same covariance matrix. So that's not going to good. I mean, it may change the mean, but it will have the same covariance matrix. Mean will be applied. I mean, u alpha. If alpha was the mean, then u alpha will be the new mean. Okay. But if you have a symplectic, that is why we need the symplectic isomorphism. If you have a symplectic isomorphism, then that will change the covariance matrix. Okay, like this. So we want to get new states using this symplectic matrix, and we want. So now first thing is we want to define some other new state. Okay, then we want to compute its characteristic function. Okay, and then we want to say that it's all I mean, at least in the n equal to 2 case, whether we can get all possible matrices. I mean, what are all possible matrices determined by the, we will come to the uncertainty relation, determined by the uncertainty relation. Okay, that's what we want. So for that, we have the following lemma. So this till now it's clear. You can just conjugate with the symplectic isomorphism and you get a new state with a new covariance matrix. Yeah. Gamma S. That's one way of we will see. Till now, we have only one Gaussian state, not one family of Gaussian state. If you forget the mean, with covariance matrix, we have only one. The vacuum, all our this is what is called coherent vectors. Okay, whatever we defined as chi x is equal to, I mean, e power non x square by 2 e of x. So this is what is called coherent vectors. So we have got Gaussian state given by the coherent vectors till now. Okay, and they all have the same covariance matrix identity, and the mean is different. So if you don't care about the mean, only the covariance matrix, we have only one example till now. Okay, now by applying this, we get a new covariance matrix, but then that will not give all possibilities. So we want to define a new state. Next thing we want to define a new state. Okay, for example, we want to define a new state, which is actually not a pure state. Okay? We will use the creation annihilation operator or what is called the number operator. I will define it now. Okay? Using that, we get a new state. Okay, and that will have some covariance matrix. Then by conjugating with respect to this, we will try to get all possible yes with determinant greater than 1. Okay? But determinant smaller than 1, there will be restriction. Okay? That we will see. Okay? So that is so. Yeah, any covariance matrix, there will be a restriction. There will be a problem. Something should be greater than one side of. Up to that, we want to get everything right. Yeah, that's what. Okay. I mean, we will prove the structure theorem. If it is Gaussian, the characteristic function will look like this. It will be determined by a covariance matrix and a mean and a vector in R. That is one way statement. And for any such thing, we want to get something. So that is that. Okay. So for that, we need the following lemma. You take, so our H is L2 of Rn as usual. Okay. And we have this coherent vectors, which is defined already. Of X. Okay. Then identity is equal to integral. I will write this as an operator integral, but this has to be made sense with weak topology. So I will write that statement also. This is just our notation. Okay. I is equal to 1 by pi to take this chi x. These are operators, of course, rank 1 operators. We have rank 1 operator. Okay. Wait a minute. This is for an, I use Z. Let me use Z. Z in CN. Okay. It will be clear. So this is the rank 1 operator. Okay, dx dy. Yeah. So R2n. I mean, I should write dx1 up to xn, dy1 up to yn. This is a Lebesgue measure in R2n. Okay. This is just the usual integration. Okay. With the usual, I mean, if functions are nice, it's usual integration. Riemann integration if you want. Okay. So it is integral with respect to the Lebesgue measure and R2n. So, but you take the operators. So the integrand is an operator. So integral is always a limit of finite sum, right? You have finite sum, which you can make sense algebraically. Okay? Then it's a limit of some finite sum. That is what usually integral is. So that limit has to be defined in terms of from topology. Okay? That topology in the weak topology. So did I say anything about weak topology till now? I have to say, did I say anything about weak topology? Not the Banach space weak topology. This is a problem in operator algebra. They have been using this, abusing this terminology. Huh? Yeah. So usually, let me have a digression. Maybe here, I should have done it here. Good. Oh, that's okay. I think I said it, but anyway, I'll recall it again. This is terminology. So if we have some, I mean, we should use net. I hope, do you know net? Even if you don't know, it doesn't matter. We will be using sequences only. Okay. But these topologies are not actually metrizable topology. So we have to use net. Okay. So I state it as net. Let me not even, you assume that it's sequence if you want. Okay. So if you have a net, T lambda, lambda in lambda, contained in some B of H. We already know, I have already defined. Then T lambda converges to T in strong topology if T lambda xi converges to T xi This is just in the Hilbert space. This is happening in the Hilbert space. Okay. So in H, converges in H for all xi. For every individual xi, if it converges, this is what is called strong topology. There is something called weak topology. T lambda converges to T weakly if xi T lambda eta converges to, this is just complex numbers, right? Xi T eta for all xi eta and H. These are all just inner product. They are just complex numbers. Those complex numbers converges to. This is what weak topology is. This is not the weak topology in the Banach space sense. Banach space, we have a weak topology. That is, this is what is called, if you want, we can call it as operator weak topology. Okay. For some reason, this is called, this says that T lambda, this just means T lambda eta converges to T eta weakly. That's what this actually means. Okay. Banach is not, this is not Banach space weak. This is what is called operator weak topology. This is used, I mean, this is the terminology is not nice, but this has become accepted. I mean, so we shouldn't change it. Okay. Better don't change it because this will come frequently everywhere. Okay. So this is not Banach space weak topology. Which is if you have a x lambda contained in X, contained in some Banach space X. Okay. X lambda converges to X weakly in the Banach space sense if phi of X lambda converges to phi of X for all phi in X star. Okay. For every dual element, if it converges, this is what is called the weak topology in Banach space. And this is not that topology. This is operator weak topology, which means that. Okay. This is not that. This just okay. So weak topology is clear. T lambda converges to T if and only if that inner product converges to that. Okay. So it is defined in this weak topology. We have, this is an identity operator. Okay. There we have an integral, which is defined in that sense. So inner product is continuous, inner product is linear. So you can actually take the inner product, I mean, the integral out of an inner product. Integral is a kind of limit of finite sum. Okay. So inner product is linear and continuous. So you can take the, so this is equivalent to saying xi eta is equal to integral over 1 pi pi. This is pi n actually, sorry, because n is there, pi n. Okay. Pi n r2n. Pi 2n or pi n, yeah. 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 If you integrate over one of them, it's in the real line, you get square root pi. So it should be correct. Okay. So 1 by pi n r2n. I just write the same thing again. Huh? Definition? I mean, this is just not statement. You shouldn't get confused with that. That's why I have done. Okay. This is not that. That is what is usually called as weak topology in Banach space. This is not that. This is the operator weak topology. If you want, we can call it as operator weak topology. Okay. So we are defining this integral in the weak sense. That means this is weak operator topology. Okay. Okay. Which whenever we use operator, we use weak operator topology. We say just weak means weak operator topology. Okay. So this is equal to xi. This operator acted on that. And so that if you call it as txy, maybe. I mean, this actually we can evaluate it. Chi of x plus iy. Okay. We actually got it as the inner product. Chi of x plus iy. Theta. This is what it means. Correct? I mean, I have swallowed one step. You have to, which is okay, which is actually, if you look at it that way, whichever the way you want, you can just, it's okay. I've used, this is okay. This is what that is equal to that, right? If you insert that rank one operator on eta, then that inner product will come out and that vector will be there, and that you will take the inner product with this. So this is equal to that. Okay. So this is precisely that. This is for all xi and eta. That is what it means. Okay. So let us just prove it. Okay. Proof. So these are all rank 1 operators. Okay, we are dealing with rank 1 operators, sequence of rank 1 operators. And rank 1 operators are has norm 1. So the whole set is uniformly bounded. Okay, this is an exercise. You have to work it out. I don't want to. If you want, you can I mean, this was something in operator theory. You have done it for strong operator, strong topology. It's the same proof. See, if this is an exercise. First, let me. I think I have given it for strong topology in the last previous semester, right? If T lambda converges to T in weak topology, operator weak topology, okay, if and only if xi T lambda eta converges to xi T eta for all xi eta in S, where S is contained in C, which is total. It's enough to verify this for total set of vectors. I mean, T lambda converges to T, and T lambda is uniformly bounded, is less than infinity. Okay. Supremum T alpha is some m. Okay. Then you will have the triangle inequality and the convergence usual. So whatever you have to do, you just sorry. Switch it on. So it's the same idea. There is nothing. You just have to use the triangle inequality and you will get it. Okay. So so it's enough to verify for total set of vectors. We have to verify that equality, and we verify for total set of vectors. Okay. So proof. So we need to verify. Let us use E of x. Okay. We need to verify E of x, okay, and chi of here we have used chi of x. No, let me use E alpha beta. Okay, integral over R to n. I'm writing the statement here, so you don't need to look at it. R to n of E of alpha. Okay. Alpha and chi of x, okay, chi of y, E of chi of z, sorry. What did I write? Xy, E of x plus z, correct. E of beta. Here d x dy. Okay, if you wish, this is the R to n Lebesgue measure is equal to E of alpha, E of beta. That's what you have to verify for all alpha, beta. See. Okay. So I will verify for n equal to 1. For n equal to, I mean, it's just same idea. It is just you have the Gaussian integral over R to n, which is equal to the pi power, pi power n. Okay, you will get that. So it will follow for the general n. And anyway, you work it out. I mean, it's not difficult. The same thing. Unnecessarily, it will be a mess here. So I will verify for n equal to 1. Okay. So actually, you can for n equal to for general n, you can write this E of alpha as E of alpha 1 times, I mean, alpha equal to alpha 1 up to alpha n, suppose. Then E of alpha will be E of alpha 1 times E of alpha 2 up to E of alpha n, right? Okay? I mean, it just gamma of Cn is nothing but gamma of C tensor n times. Okay, so you can write it like that. Similarly, you can write this vector also tensor product. That's also not tensor product. That's also tensor product. Inner product will break up in tensor product. Okay, and they are product of functions, n functions. So the multiple integral is just the product of all the iterated integrals, right? So it follows for n equal to that. So the proof is clear for general n. If you use the tensor product everywhere, you have to use the tensor product. E of alpha will be tensor of, I mean, E of alpha 1 tensor E of alpha 2 up to E of alpha n. Similarly, those coherent vectors, which are also exponential vectors, which has a multiplied by something, which will also decompose, I mean, which is also factorize. Okay. So we will get the product, and the integral is actually a product. The iterated integral is actually a product. So it will form. Okay. So it's enough to verify for n equal to 1. I don't write all these things, so it's all clear. Okay. Okay. So for n equal to 1, so we want to verify this. Okay. So this is equal to, let us just compute the inner product. Okay. And I call Z is equal to x plus Iy. Okay. So that I can write it as, so there will be e power minus x by 2 here, e power minus x z square by 2, I will get in the first inner product. And there is another e power minus z square by 2, which I write it as e power mod z square by 2. I mean, it should be inside the integral. Okay. There is a 1 by pi. I forgot 1 by pi. Okay. 1 by pi into integral over R2. I'm just writing it as for R2. And e power minus, maybe I'll write it as x plus I by square by 2. And there is no 2 because there are 2 of them. Okay. 2. And what is the derivative? So which is just x square plus y square, right? Okay. I mean, from here I get an e power minus x square plus y square. Here I get another e power minus x square by 2. So I'm just writing it. I mean, together I get one of them. Okay. Okay. Plus the inner product between alpha and x plus iy, which it's all inside the inner product between alpha. So this is just alpha bar. The inner product is, this is just in one dimensional alpha bar x plus iy. Okay. And plus x minus iy into beta. That's all we have, right? Then dx dy. Correct? That's what I have. It reduces this, right? So shall I point out here? See, see. So here this is just e of x plus iy multiplied by a norm. And here I have the same thing, which I have got it here. Okay. Then you have to take the exponential of the individual inner product, which is the inner product of this, and this is alpha bar x plus iy. Here, these two is x plus x minus iy times beta. So that's what I have got. Okay. So we have got everything. So that is equal to 1 by pi to integral over r square. I mean, now it's you have to write it as x minus. So maybe I'll change it here itself. Okay, I'll write it once again. So, square plus y square. I want to write it as x times alpha bar plus beta. Alpha bar plus beta, no? Correct. And plus plus y into alpha bar minus I beta. Right? Okay. Now that is equal to 1 by pi. Because I'm doing this because I'm going to ask you to evaluate a different integral. Okay. That's why I'm doing this. This is simpler than that. That is more messy. So I will ask you to do it as an assignment. Okay. So which is very important. Okay? This is also important. But that is regarding a state. So I will ask you to do that. Okay. So this e power minus x square plus y square. Okay. So this we can write it as x minus alpha So I call it as lambda square plus y minus I mu minus plus y minus I mu wholes. Here also.
So this entire thing is just product of x plus I by comma like alpha plus x plus I by plus alpha plus beta or something like that. Maybe I just
No, you want to get it as a Gaussian integral. You want to use the following. Okay, e power minus x square plus y square dx dy, okay, over R2n is equal to pi. You want to use this. Okay, this we want to use. So I'm just using change of variable to get this. That's all. So I get lambda y and mu iy square. So plus we will get a plus lambda square minus mu square. Right there. No, it will be 2 lambda square. No, it will be lambda square. So where lambda equal to alpha bar plus beta by 2, right? Because we will get 2 times that. And mu is equal to alpha bar minus I beta by 2. I think I'm correct, right? X square plus 2 times I lambda y, 2 times lambda x, which is alpha, 2 times lambda x is alpha bar plus beta by x, right? Similarly there. Okay. So this we can take it out. This lambda square minus mu square will take it out. Okay. And which is just e power lambda square minus mu square times something 1 by pi times something, which is the Gaussian integral up to change of variable. Okay. So which is 1. When I divide it by 1 by pi, it's 1. So what we have is alpha bar plus beta square by 2 by 2 minus alpha bar. I will go away anyway. No, I mean it is just my. No, there is no I. I square is minus 1. No, that is why I have written minus mu square here. Okay, that is because I square is minus 1. Alpha bar minus beta by 2 whole square, which is equal to E of, I mean, which is just, there is a 4 and 4 times alpha bar beta will get. So which is just alpha bar beta, which is E of alpha, E of beta. Okay. You want to see anything? This is clear. Okay. It's just change of variable and then use that, you get this. Okay. Right. Okay. Okay, so we have proved this lemma. Okay, so instead of identity, we can insert this integral anywhere you want. So the corollary to this is rho hat of alpha, anything is equal to integral over R2n 1 by pi power n. Okay. X rho W of alpha K of x. K. Okay. Why is this true? This is because proof is clear. Rho hat of alpha is equal to trace of W of alpha rho. Okay. Now instead of identity, I insert that integral. integral 1 by pi power n pi x kx. I insert that integral times rho. Okay. Now trace is linear and trace is also continuous with respect to once you have one operator there, and I mean this is true, no? If you have this is in the exam, as I said. It's also an assignment, I believe. T lambda converges to T weakly, which is what in the exam we proved. Then trace of some xt lambda converges to trace of xt for all x trace class. If you have a trace class operator x, T lambda converges to T, then trace of this converges to this. This was in the assignment also, I believe. This was in the exam of graduate analysis. So because of that, this is equal to you can take the integral out, and integral is linear and integral is weakly continuous for us. So you can take it out. So integral over R2n 1 by pi trace of, you can take the trace inside, which is going to be what we have is the following. Then we can take this. This is the trace of W of alpha rho doesn't matter whichever the way I am. And that is precisely equal to, you can, what is the trace. When you have a rank one operator like that, we have calculated the trace the last semester. It is like the column vector. When the vector, you can just take it to the other side. That is because we have proved it. Okay, it's not. That is not the statement. It's not the same statement. They are not considered as operator. We have proved that if you have a rank one operator, then you can write the trace as an inner product. This is equal to inner product of integral pi power n R2n, then inner product of kx w of alpha rho. It just doesn't matter. Rho by alpha, w of alpha doesn't matter. Rho x. Okay. So we approved it. So this is what we will use. So if you want to compute the characteristic function, this is rho hat of alpha. Rho hat of alpha is exactly this. Okay. And this is dx dy. Maybe I should use z here. No. All these places it should be z. And dz, then dx dy. Dx dy. Okay, clear? No problem. So we want to use this to compute the characteristic function of the state we are going to define. So to define that state, we still don't have a name for it. Yeah.
So we are saying that all these coordinate states also a basis of the.
No, this is coherent state anyway from a basis, right? They, basis means what? It's a, it's not orthogonal. The inner product between any two coherent vectors is not zero. Coherent vectors are some constant multiple of exponential vectors. Exponential vectors are linearly independent and they are total. It's not a basis anymore. It's called what is called Schroeder basis or something. Basis means linear combination should be everything. which is not the case here. This is not a basis. Orthonormal basis is not a basis.
Yeah.
Orthonormal basis, you have to take the span and you have to take the closure. Here you have to take the span and take the closure. It is just, it's not orthogonal to each other. Okay, it's not, these vectors are linearly independent. They are not orthogonal to each other. It's a linearly independent set whose span closure is everything. It's not a basis. That's what totality means. We call it total, right? Linearly independent and total. But that is anyway proved. This integral is something else. This is for operators. This integral says this is something more. You can write anything, any operator. I mean, you can write identity as this. Huh? Say it again.
If I have some closures that are maybe not on the basis, then I can write identity like this.
Orthonormal basis for what? The CN.
No, not CN. Like, the operators are
No, for the Hilbert space, for the Fox space.
no.
If you have, but where does it come into picture? I don't understand the question. What is the question?
No, like what I'm saying is we have the covariance space and the Hilbert space.
Right.
So instead of that, we take some other basis, like the orthonormal basis.
Correct. Okay.
So then also can we write the identity like this?
No.
Because I think in physics we use this.
No, like you said, a basis per h, orthonormal basis per h. You can write identity as integral of outer product, like you index the basis by r, or like some.
Yeah, that is true.
Yeah.
That is true.
Like spectral decomposition of identity.
Yeah.
Which will give you one example.
But then you have to see how you make sense. Yeah, it's again the weak topology, it can make sense. But in the norm topology, it is for the Hilbert-Smith, all Hilbert-Smith operators will get. I mean, that you don't need to take integral, you can take the sum itself. Every Hilbert-Smith operators, this EI, EJ, the rank one operators, they are we have seen it, that forms an orthonormal basis for the Hilbert-Smith operators. So if you use the integral in the weak sense, you will get every operator, correct? Huh? Square, I mean, T star T is trace class. T is Hilbert-Smith. T star T is trace class. If you want to, Hilbert-Smith operators is omnipresent everywhere when you want to do this theory in infinite mode, infinite dimension. We are using Cn, no? If you have gamma of h for infinite dimension. So whatever you want to do, Hilbert-Smith operator, that condition will come everywhere. So it's very important. Hilbert-Smith operators. Okay, so we have proved this. Okay, this is very similar to what you said. Yes, correct. Okay. Now we want to define a new state. For that, we want to define what is called a number operator. We can directly take that number operator, or we can use this definition. So let us take gamma of C. Okay, let us take n equal to C. Let h is equal to gamma of C, which is L2 of R. Okay, which is L2 of R. So n equal to 1. Okay. Then gamma of C is nothing but you have to take the symmetric tensor product and direct sum, but everything turns out to be C, right? Like this. Okay. On this, but then the nth C, which is the nth particle space, is C tensor C n times. But then it is C again. But then if you take a Z, you will, this ZC, you denote, you write it as direct sum of C chi n. Okay, where chi n, you can, if you want, you can call it as 1 tensor 1 tensor up to 1 n times. Where 1 is the number 1 in complex number. 1 is, this is not identity or something. 1 is in C. I mean, for us, even in the general Fock space, the first 0 particle space is complex number. Okay, there you take the vacuum vector E of 0 is just number 1 in the complex number. Okay? That's what we are taking. So here we gamma of C looks like the C direction, C. Okay, you take the nth one direction, one tensor n with the nth with unit vector, which is unit vectors. You call it as chi n, okay, which is in that. Then Z tensor n is nothing but Z power n, right? Which is a number times chi n, right? Because you take Z tensor, you take the Z out and it will be Z n, right? So E of Z will look like summation. You want summation or direct sum? I mean, they doesn't matter. Okay. I mean, which you can call it as L2C also if you will. Okay. Which is summation Z power n chi n as a vector. Chi n is a vector in the n direction. So you can write it like this, divided by square root of n factorial, right? E of Z by definition is this, name. E of any vector Z is equal to direct sum of Z tensor n, which is a symmetric tensor, divided by n factorial. This is how E of Z is defined initially for the Fock space. Okay. So here in this picture, E of Z look like this. Okay. Now you know how the creation operator, annihilation operator acts. Annihilation operator brings the nth particle space to n-1 particle space, but it multiplies by a n power half. Okay. So you take the annihilation operator corresponding to A of 1. Okay, let A equal to A of 1. 1 is in C. Okay. Creation operator. So similarly, A dagger equal to A dagger of 1. Again, 1 is in C. Okay. So then A of Z power n. I mean, A of chi n, let us see. What is A of chi n? It's enough to see what is A of chi n. A of chi n, you can, I mean, Z power n will multiply by Z power n. Okay. These are all linear operators anyway. They're unbounded, but linear operators. Okay. So A of chi n is going to be n power half. This was an assignment last, right? From the bigger space to it will come to this. Maybe you didn't write because you didn't take it for credit. You didn't give it. You compute the creation annihilation. See, let me write it. Maybe I will recall the whole thing. Actually, these things are not needed for what we are going to define, because what we need is what is called a number operator. It will turn out that this is the number operator. So that is why you just recall it. Okay. See, we have P alpha. Okay. P alpha is something which is defined by I, T, W of alpha, right? Right. Then you can define Q alpha equal to minus of P of I alpha. Then the creation operator A alpha is defined by Q alpha plus IP alpha. Okay. And the annihilation operator A dagger alpha is given by Q alpha minus IP alpha. And the assignment last year was A alpha. So we know how P alpha, Q alpha acts on exponential vectors. Okay. I mean, that also I should recall. It's not clear. We have to differentiate it, and that only you will get. Okay, let me just recall all these things. P alpha acting on exponential vector Ex is equal to, no, I mean, you can directly, that will be linear combination of these two things. Okay. So let me just write what is A alpha. A alpha acting on E of X will be alpha X E of X. That's all. Of course, on the total setup in the linear combination, you have to take the linear combination. Okay. And A dagger alpha acting on E of X equal to, it is actually the P symmetric vector of E of X tensor alpha. But that is equal to d by dt E of X plus alpha, X plus T alpha, sorry, T alpha, okay, at T equals 0. You will get all these things by the definition of P alpha, then whatever we have written, if you use that. Okay. If you use again derivative differentiation and all that, because any nth particle vectors, for one particle vector, you get it by differentiating the exponential vectors. Okay. It is true that x tensor n equal to, I don't know whether I will write it correctly, x tensor n by n factorial is equal to E of x minus summation n equal to 0 to n minus 1, sorry, j equal to 0 to n minus 1, x tensor j by j factorial, right? Is that right? You remove that, huh? And you need tx, sorry, you need tx here, tx. And then you have to differentiate n times, okay? That's all. If you differentiate you take the exponential vectors, you take etx as a function of t, okay? Etx as a function of t, differentiate it n times, and apply t, and then evaluate t equal to 0. That whatever you get, evaluate t equal to 0, you get the nth x tensor n divided by n factorial. Okay, this is just d, whatever it means, d n by dt n at t equal to 0 is x tensor n by n factorial. Okay, now you use this to verify that a dagger of alpha acting on E of x, okay, E of x, not E of x, the n particle vector. This was an assignment, x tensor n is equal to n power half x tensor n minus 1, right? Right? This will be. And a dagger alpha acting on S tensor n is equal to 1 by n plus 1 power half, okay, summation x tensor r tensor alpha tensor x n minus r, x tensor n minus r, okay. So this is r equal to 1 to n. This is a symmetrization. What you do is annihilation operator annihilates one of them. Okay. Sorry. Here you have to have inner product. Sorry, forgot the inner product. Alpha x. It annihilates one of the vector and brings it down. Okay, that is what the annihilation operator. Creation operator attaches the alpha, but you can't attach arbitrarily. You have to symmetrize the whole thing. It's symmetrizing. Okay. So that is a. But there,
it's very small, but it's not the nth derivative, it's like the nth iterated derivative.
Nth iterated derivative.
It's not dn by dt to the d by dt n times.
D by dt n times. What is the difference?
If dn by this is you differentiate d by dt with respect to t again.
Correct.
Okay, fine. It's the same in this case, but
yeah, it's not total derivative. It's not like there is no total. Yeah. It's okay. It's okay. Huh? Say it again.
This A dagger should start with R equal to B.
R equal to 0. Correct. R equal to 0 to correct. Because there are n minus 1 terms, right? R equal to 0. Yeah, no problem. So, yeah. Okay. So the whole thing turns out that in this case, when gamma equal to C, okay, H is equal to gamma of C, okay. Yeah.
When you write A alpha acting on X tensor n, do you mean that the other terms will be directly conjugated?
Say it again. You write A
For X tensor n. So, do you mean all the other terms?
What is the other term?
For the elements should be the direct sum of the products.
Yeah. This goes to the other things are 0. Correct. Yeah. Sure. Yeah, correct. That's what it is. The direct sum. When it is in the nth particle space, we just write the nth particle space. Correct. Yeah. The direction is correct. When gamma equal to when our space is gamma of C, okay, when it is n equal to 1, then A of chi n will be n power half chi n minus 1. Okay. Which is clear because inner product between 1 and 1 is 1 and we get 1 power n. And A dagger A of chi n okay, which is going to be chi-n minus 1, you will take it to the top, take it to the 1 plus 1 particle space. Okay, that will become chi-n minus 1. And that will become n power half into this n times chi. I mean, here the n plus 1 it should be, but it comes from n minus 1, right? A dagger acting on chi n minus 1 will be chi n power half times chi n. Okay. Why you get n power half? Because see, 1 by n plus 1 half is there, but there are n terms. So there you get it n in the top. Okay. Because of that, you get this. So A dagger A acting on chi n is n times chi. Okay. This is just nothing. This is just on the nth particle space, it acts as n, the number n. Okay. This is what is called number operator. You also call it as n, or you use the name lambda or n or whatever. Okay, let us use A dagger. A dagger is what is called the number operator. Okay, and A dagger on the nth particle space, its value is n, which is A dagger A chi n equal to n times chi n. And you see that chi n is an orthonormal basis, right? N union 0, of course. Orthonormal basis for gamma of C. Okay. So all these chi-n's are eigenvectors. Okay. Eigenvectors, the eigenvalue is n. Of course, n is blowing up, so it's certainly an unbounded operator. This is only defined on number operator is defined on the linear span of the finite particle space. It's not extended to the whole. The direct sum is actually the closure of all linear span of finite particle vectors. So the Fox space is C direction, C, which is L2C. You can have an infinite tuple, but you can't have an infinite tuple here because the operator will blow. This is just this linear span, just the span of all the finite particle space. You don't close it. Okay, that is the domain for this number operator. Actually, you can have a bigger domain also. You have exponential vector and all that. But for the number operator, it is this. Let us take this as our operator. Okay. Okay. Now, let us consider this e power minus s A dagger n, A dagger A, which we can define, okay, on eigenvectors, which acting on any chi n is equal to e power minus sn chi n, right? Right? That is how it acts on the, this is a functional calculus kind of thing, okay, e power minus sn, okay. So then the trace of e power minus s A dagger A, this operator, this is a bounded operator. Of course, trace itself is finite, means the bounded operator, of course. Okay. This e power the eigenvalues are bounded, it's bounded. Okay. Then the operator is bounded. Okay. It's a bounded operator. That is equal to summation n equal to 0 to infinity e power minus sn. Right? This is the sum of the eigenvalues, is the trace. Okay. E power minus sn. And this is just a geometric series. Okay. With the first term is 1. Okay. And the R is 1 by e power minus s. This is equal to, this is the trace. So 1 by e power minus s into e power rho equal to 1 minus e power minus s e power minus s A dagger A. You take the exponentiation of the number operator is a state. Okay. H is equal to gamma of C. Is a state on gamma of C. Okay. Now we want to compute the characteristic function of this state. So we have got something, so proposition. Which is also assignment. Which is same as the Gaussian integral we have. Okay. Except here there will be more messy terms. The idea is same. You have to use just the change of variable formula, and the idea is same. use the Gaussian thing, you will get it. Okay. So rho hat of alpha, the alpha is in C now. Rho hat of alpha equal to 1 by 2 cot is cot hyperbolic, which is just e power x minus plus 1 by e power x minus 1. Okay. Cot square s by 2, I think. Oh no, is it like that? Cot is cot h, which is e power cot hx is e power x plus 1 by e power x minus e power minus x minus 1. Yeah, it will be same as e power 2x you will get. So I have s by 2 here. Because of that, it will, yeah. Right? Yeah. I think it is cot h square s by 2. Okay. No, so where is alpha coming? Wait. So let me call it as rho s. Okay, rho s. This times, no, I think it should be inside, no? Let me just look at it. I forgot. Is this like this? So he also hasn't given the whole calculation. Yeah, sorry, it should be inside e power. Exponential minus half cot h s by 2. So this is, I mean, this is a sigma. That's what I want to say. This is a sigma cot s mod alpha square. Okay. See. And s is greater than 0. We are using s greater than 0. Of course, we want to get a bounded operator, so s should be greater than 0, right? Okay. I mean, this is only when s is greater than 0. This is e power minus s a dagger a is a bounded operator. S is less than 0, that will be positive, that will blow out, right? So proof is, of course, this assignment, but there is no complication, I believe. We have that rho s hat of alpha is equal to 1 by pi integral over R2. Okay. We use the coherent vectors chi of x plus iy. You have to evaluate that. Rho s w of alpha, rho s chi of x plus iy, linear product dx dy. Okay. Now this w of alpha, you know this, you can, I mean, this coherent vectors, you write it as exponential vectors, constant time. So you get a e power integral over pi, e power minus, let me write it as mod z square by 2, you will get. And then e of x plus iy. I write z is equal to x plus iy. Okay. E of x plus iy. Okay. Then this w of alpha also you expand. I mean, then you e power minus alpha square by 2 minus alpha bar z. Okay, you get all those things. Then e of z plus alpha you get, right? Z plus alpha you get. Then you have a rho s. Rho s is positive. You can bring the rho s here. Okay. Notice that this is only you have to notice. Rho s acting on e of z is equal to e of e power minus s z. Okay. So you apply the e power minus s z. Then you expand the whole thing. You will get some square times something, which you have to write it as e power minus x square plus y square. In that form, change of variable, and then everything will cancel. Okay. And you get the answer. Okay, so this is the assignment, some messy thing you have to do. Okay. So I think it's stop here. So we will play with this